With circle geometry, turn your books to page 10, where you'll find a summary of all your circle theorems. Okay, but now before we do the circle theorems, I want us to quickly go touch on some circle terminology. Okay. First question, very simple one. Okay, that's more like an egg. What is a circle?
It's how do you make it with no corners?
360 degrees.
What is the shape of no corners? Is that a circle?
No.
Okay, what's a circle? Well done. Okay, so a circle, right, can be defined as a set of points. Think back to functions. Okay, a set of points that are all equidistant from another point called its center. So if I started off and here's a point that I called the center, and I drew a point 2 centimeters away from that one there, another one 2 centimeters there, and I kept on going, I will end up with so many points that they all just form a circle, because they're just a whole bunch of points that are all the same distance away from my center, right? What do we call that distance?
Radius.
Thank you. So from my center to the circle, we call that a radius. Cool. Now, the radius is your line segment joining your center of the circle to any point on the circumference. Yes? Okay. What is a chord? Anyone? Okay, so a chord is a line segment joining any 2 points on your circle. Does that make sense? Okay, the one thing I want you guys to make sure is, make sure you know the difference between a line segment, and a ray. Right? Remember, a line has no start point, no end point. It just continues forever in both directions. A line segment has a definite start point, a definite end point. So if you look at a chord, it starts there and ends there. Radius starts there, ends there. So a radius and a chord are all line segments. And a ray starts at a point and continues forever. It's got a start point, no end point. Makes sense? Cool. And then, what is the circumference? It's not that hard, guys. What's the circumference?
The edge of
The distance of the...
Yeah, the distance of the perimeter of my circle.
Yeah.
Right? Cool. That's our circumference out there. And then what's an arc?
A section. The distance from one point to the other.
Yeah, so so imagine I've got 2 points in my circle. It's now the perimeter or the distance you'll travel along the circumference of the circle from one point to another. That's an arc. That makes sense. Okay. And then, what does it mean if I say something subtends another? Let's say I say this line subtends an angle. What does that mean? So if I've got line AB, and I say it subtends angle C. Yeah, so if I sort of extend, if I draw lines from A to B and they meet at a point, right? So subtends is another word for like almost like supports. So line AB will sort of support that angle over there. Okay? So line AB will subtend angle C. Line AC will subtend angle B. Line BC will subtend angle A. Does that make sense? So when I speak of this certain chord or this arc subtending an angle, it means now at the base or where that angle is formed, you will find this line or this chord or this arc. You guys with me? Okay, fantastic. And then what's the diameter? Please don't say twice the radius.
2 times the radius.
Okay. Remember, so I said a chord is a line segment joining any 2 points on my circle. Right? A diameter is a chord that goes through my center. Okay. So diameter is a line segment joining 2 points on my circle while going through the center. Does that make sense? So I want you guys to get used to the terminology we use with circles so that when we get to the theorems, things don't make tons and tons of like confusion in your head. Yes? Cool. Can I erase this? Now in your books, we're going to quickly just go through all the theorems, and then I'll show you how to sort of go about with these questions. Okay, so let's look at some of our theorems. Line segment through the center and the midpoint, right? So that, what does that say? That if I draw a line segment that goes through the center of my circle and through the midpoint of any chord, it will be perpendicular to that chord. Yes? So if I've got a circle there, I draw a line from center and I've got a chord here. And here's the midpoint of that chord. If I draw a line from the center, midpoint, that line segment will be perpendicular to my chord. Does that make sense? Okay. And then the converse of that one again would be the perpendicular bisector of a chord will go through the center of my circle. So if I didn't have this line initially here, and I just said, well, here's a line that will bisect my chord, go through the midpoint, that's what bisect means, and is perpendicular to my chord, it has to go through the center. Does that make sense? So if I draw a line from the center to my chord, like directly through the midpoint, it will be perpendicular to my chord, right? Or if I said a line drawn from the center of the circle, perpendicular to a chord, will bisect that chord. Those are all ways you can use that theorem. Does that make sense? Okay. And then everyone gets this. Who doesn't get this fully? Awesome. Okay. Then we look at now, angles obtended by a diameter is always a right angle. So if I have a circle here, and you're given a diameter, and there's any angle obtended by that diameter, it will be a right angle. Always, always, always. Yes? Fantastic. And then on your next page, page 11, angle at the center is twice the angle at the circumference. Very important, they must be in the same segment. What's a segment? It's the side of the circle, right? Demarcated off by either a chord or an arc. Okay, so let's sort of look at example of that. So this is my center. We've got point A there and point B here. And that sort of now does that there. If this is x at the top here, this is going to be 2x. That only works, so if I look at my chord or my arc, if this is the chord AB, the chord breaks up my circle into two segments. Here's the one segment, there's the other segment. The small segment's called your minor segment. The big one's called your major segment. Yes? Okay, so now these two angles have to always be in the same segment. So they're both in the major segment. Cool. But now if I were to do this and draw an angle at my center and an angle on the surface, here's my chord, AB. If this is x, this angle is not 2x because they're in different segments, right? So which angle will be 2x? The reflex angle. So this reflex angle here will be 2x. You guys with me? Okay.
Isn't that another theorem though?
Which other theorem?
I mean, that you just showed.
No, it's angle at center is equal twice on the circumference. Okay. So if it's like this, the reflex angle. If it's like that, then it's going to, if you see the sort of the Star Trek sign, then you know, okay, cool. These two angles, that will be the small one, that will be the one that's twice the small one. Makes sense? Fantastic. And then we go through now number 5. Angles in the same segment are always equal, right? Now what's the full theorem? Angles that are subtended by the same chord or arc in the same segment will be equal, right? Or angles that are subtended by in the same segment will be equal. Let me give you guys a few examples. So the minute we see a bow tie, or butterfly as the girls say, guys always say bow tie. So you see one of these. Okay? You automatically, if that is x, that will be x, right? If that is y, that will be y. Because now if this is my chord, and I've got another chord somewhere there, these angles are subtended both by this chord here, like that. These ones are subtended by that chord there, like that. Right? So now, and they're in the same segment. Therefore, they will be equal. So now, if I were to draw this, here's a chord. It subtends this angle here and subtends that angle there. These angles are not equal. They are subtended by the same chord, yes, but in different segments. You guys get that? So they have to be both in the same segment to be equal. If they're in opposite segments, like these two here, they will not be equal. That takes us to like cyclic quads, and we'll get there. You guys with me? Okay. Okay. Also, another sort of version of this is, like I said, if we've got angles subtended by chords of equal lengths, they will also be equal. So imagine I've got this set up here. I've got a chord here subtending that angle there, and I've got a chord here subtending that angle there. If this line is equal to that line, this angle has to be equal to that angle there. Does that make sense? Imagine if I took this triangle and sort of just twisted it around. Because the chord is the exact same chord, same length, the angles have to remain equal. So if your chords or your arcs are the same length, your angles have to be the same size. You guys with me?
Yeah.
Fantastic. Can I erase some of the stuff in the meantime? Cool.
With that last one, would the theorem be angles in the same segments are equal?
Yeah, say angles same segment, or say angles subtended by equal chords or arcs.
Okay.
Cool. Okay, now looking at our next theorem, which is now cyclic quads, right? Now cyclic quads can, well not, they can't really get hairy, but students tend to make them hairier than they are, right? And cyclic quads are really like stress-free. So if we've got another circle, and I put a cyclic quad, keep in mind, a cyclic quad must touch all four sides must touch my circle, right? They give you examples where they'll say, is this a cyclic quad? And it's like just a random quadrilateral somewhere else. Even though it doesn't touch the four sides of that circle, but there will be a circle that I can draw perfectly around that cyclic quad. So sometimes if I were to give you a circle that looks like this, sorry, and then draw a quad from the center, and they say prove that that is a cyclic quad, and you do prove it, it's a cyclic quad not of this circle, but of another circle. Do you get what I'm saying? There will be another circle that I can draw that will fit perfectly around that quadrilateral. Does that make sense? Okay. But otherwise, if it isn't proven, you can't use cyclic quad properties on something like that. If it clearly looks like a cyclic quad, you can use those cyclic quad properties. Okay. So with this one, first one is, if this angle is x, and that angle is y, x plus y gives us 180. Opposite angles of a cyclic quadrilateral are supplementary. They add up to 180 degrees. Okay. What else do we know? If I've got an exterior angle of my cyclic quad, this one here, it's equal to the interior opposite angle. Make sense? Okay. Fantastic. And that should be the next theorem there. Okay. And then we have that table, which is very important on page 12. This table is incredibly, incredibly important because it tells you now, how do I prove that something is a cyclic quadrilateral? And people sometimes have trouble with this, okay? So again, you can prove either that opposite angles are supplementary, right? If you can prove that the angles are in the same segment, the whole angles in the same segment are equal, if you can prove that, the points that sort of form those angles will be a cyclic quadrilateral. Because if I draw the diagonals of a cyclic quad, like that, what do I have? I've got bow tie, there. And then I've got angles in the same segment. Okay, so if you can prove angles in the same segment, that thing will be a cyclic quadrilateral. Makes sense, okay? And the last one is proving, obviously, the exterior angle of a cyclic quad. And usually when they try to trick you, they'll give you angles in the same segment more of the time. And then they say, prove a cyclic quad. And because we weren't sort of thinking in that way, we tend to just oversee it because we're trying to find the exterior angle or try to find the opposite angles of the cyclic quad. Keep in mind this angle in the same segment. That's a very important one. That's usually the one that ends up being your proof at the end of the day. Yeah? Okay, then number 9 we get to our tangents, right? So the first one we know is that tangents from the same point will be equal. So if I have a tangent from a random point up here, that sort of goes like that, and like that, the distance from there, so if this is A, B, C, this will be equal to that. Yes? Okay. And the last one is my favorite, the tan chord theorem. Okay? Now the tan chord theorem, if I've got a circle there, and I've got a tangent to my circle coming that way. And then you've got, at the point where it's tangent, you have a chord that subtends an angle inside my circle. Use colors now. So at that point, the tan chord theorem states that the angle between my tangent and my chord, so this angle here, you guys see that? Okay. So that angle there between my tangent and my chord is going to be equal to the angle subtended by that very same chord in the circle in the ultimate segment. So it's not going to be in the segment where this angle is, but in the other segment here. So when you see this angle go inside the triangle and in the opposite way, that's the angle that it'll be equal to. Makes sense? Okay. And whenever you see a tangent in a chord or a tangent in a triangle, there's always two tan chord theorems. So then there's the other side, which is this and that. And this is the one theorem that students tend to sort of struggle applying, the tan chord theorem. Okay. So whenever you see this tangent chord, all you need to do is then say, at the chord, whatever angle that chord subtends on the other side will be equal to the angle between my tangent and that chord on both sides there. Yes? Yeah. Okay, fantastic. Cool. So those are our circle theorems. Now, the best thing I can tell you about this, circle geometry is very much like proving identities in trigonometry. Right? There's no set method of do A, B, C, D, like if I'm solving an equation. Take my variables to the one side, divide by whatever, and minus this. So with this, it's all the problem-solving kind of stuff that comes into play. So the key things about this is if you turn now to your next page, which is page 14, it'll show you how to answer these questions, right? And now answering these questions, you need to do one thing. Initially, with every question, they'll give you a bit of information at the top that AB is parallel to BC and blah, blah, blah. They'll give you a whole bunch of information stuff at the top. Then you'll see it'll say 1.1 or like A or something like that. From like 1.1 or A or whatever, that's when they actually ask questions. Do yourself one massive favor. Do not read that before you've actually fully looked at the circle. So when you start off, take your pencil case or anything, cover the part where they ask you questions. Only look at the information they give you. And as they give it to you, plug it into your diagram. So fill it in your diagram, fill in all the information they've given you. Once you've filled in everything you can, take colored pens or pencils, and try find all the theorems you can find, and try say, that's equal to that, and sort of use the same color. If this is equal to that, make it like red and red. And if that's equal to that, make it green and green. And do as much coloring in as you can before you start the question. Because what happens is, when you start the question, and you sort of read the question, then look at the diagram, you have what they call, it's either called presque vu or jamais vu, which is the opposite of déjà vu. When something that, you know, I should know this thing, but it sort of goes away. But déjà vu is, I know this hasn't happened before, but I feel like it has. And jamais vu or presque vu is one of those, but I should know this, but it's just, it's gone in my head. Okay, so then prevent that mental block by first trying to find everything you need to. Because the minute they say, look for this, your mind just blocks it all out. So you can see everything but the one thing they want you to find. And that's where circle geometry becomes a bit difficult. Not because you don't understand it, but because those mental blocks. And if you sort of apply this method, you'll find that actually, more of the time, you'll see more things before you start. Things that you weren't really sort of worrying about. Make sense? Okay, let's now try some examples, and then you guys can do an activity afterwards. So let's turn to, on page 14, quickly just erase the board. On page 14, they give us this diagram. I'm going to try to draw it as best as I can in the top right corner. Okay, that's P, 1, 2. That's 2, 1, W. That's 1, 2, 3, and that's S, and this is angle R. Okay, now in the diagram, O is the center of my circle, so this is O here. Sorry. Okay, PWSR is a cyclic quad. PWSR, that kite, it looks like a kite type thing, is a cyclic quad. And then PS, WO, and OS are drawn. They showed you the angles, the lines there. PW is parallel to OS. So this is parallel to that over there. P is 36 degrees. Told you that this now. Angle, sorry, P1 is 36 degrees. Okay. Now the next thing is, do not read what they want you to find out. Okay? Read that top part again. Make sure you filled in everything that they've given you. Once you've read it a second time, look at the diagram. And let's try find things that we can fill in ourselves now. Okay? Where don't get tricked into using angles in the same segment. Right? These points, this point is on the circle, on my center, not on the circle. If this point was here, we could, but now we can't use angle in the same segment there. Right? Okay. So then the other things we can look at are, we got parallel lines. So know that this angle here has to be equal to this angle there. Right? You guys with me?
Yep.
Okay? I know that,
P1 exists.
yeah, P1 is equal to, well, it's in black. Let me use black as well for that one. So this angle that's in black, I'm going to keep in black. P1 is equal to S2. And then, that's now alternate angles. And then we find that these are vertically opposite, those are vertically opposite as well. Here's another one. Look at chord WS. O is an angle on the circle, subtended by WS. But WS also subtends angle P1. So then we know that O is going to be twice P1. Right? So I know already that. I'm going to put that here. O is going to be equal to 2 times angle P1. And then, can you guys see anything else? Anything else? Okay, so we know we've got a cyclic quad. We know that this plus that's 180, this plus that's equal to 180. And then, once you've seen everything that you can see, yes?
Is S2 not equal to W2?
No.
That's
Why would you say S2 is equal to W2?
same. Okay.
Okay, remember what I was saying now is don't get fooled into thinking that these two are angled in the same segment. Because they're not subtended by the same chord.
So both ends have to be on the same side.
Yeah, so when you do angle in the same segment, your bow tie, or this sort of butterfly thing, must touch the circle on all points. So because this one end is on O, these two angles are not equal. If this point was here, yes, they'd be equal. But in this case, they're not equal. Does that make sense? Any other statements, questions? Okay, sweet. Now let's look at what they're asking us to find out. Calculate the sizes of the following angles. SOW. So that's SOW, angle O over there. And we know that angle O is equal to W2. And I said angle O is equal to twice P1. Why? Because angle at center is equal to twice the angle on the circumference. You see how now, a lot of the questions I ask you, you would have seen that stuff before you even started. Right? So then we can start by saying angle SOW is equal to 2 times angle P1, which is 36 by 2, 72. 72 degrees. What's our reason? Angle at the center is equal to 2 times the angle, on my circle. Okay, I'm going to write in shorthand for the sake of space. Angle W2, where's W2? That's there. And we already said W2 is equal to angle O there, right? Then we're going to say, so this is number 1, number 2 is angle W2 is equal to angle SOW. Reason?
This is
Alternate angles, because the lines are parallel. Okay, so our reason is alternate angles. And then whenever you say alternate angles, you have to specify which lines are parallel. You can say PW is parallel to OS. You guys still with me? Yeah. Okay, let's find angle OSW. OSW. How will we find OSW? this angle at S1 and 2.
We know S2 or
Well,
S2.
you could.
We know what S2 is, right? Right? 72 degrees.
Yeah.
Okay? Now, what do we know about line OW and OS?
Radio.
They're radii and they're equal, right? Meaning this has got to be
S1 is-
an isosceles triangle, right? So then we know that angle W1 has to be equal to angle S1 plus S2, the OSW, right? Because of isosceles triangle. You guys with me? Okay, so now let's look. If this is 72 over there, we know that this is 36. Whatever these two angles are, they must be 180 minus 72 and you divide them by 2. Because of angles in a triangle. Okay, so then I know that, okay, angle SOW worked out before, plus 2 times, I said W1 is equal to that already. So 2 times W1 is got to be equal to 180 degrees, angles in a triangle. Then we can just simply work it out. We say this angle is 72 degrees, so take it across, we're going to get 2 times W1 is equal to 180 minus 72, that will give us 98, right? Yeah. So then W1 is equal to 98 divided by 2, that gives us 40
It's 108 divided by 2.
102. Well,
108 divided by 2.
sorry, thank you.
108.
108, not 98. It's 108 divided by 2, that's 54. Okay? Therefore, W1 is equal to 54 degrees. Which is equal to S1, S2 anyway. Okay, you say S1 plus S2 is equal to 54 degrees. You guys still with me? Okay, fantastic. Then, so 7.3 here. So that's 3 there. And then we need to find now the angle R down here. Right? Yeah?
Yeah, sorry.
Okay. We need to find the angle R. So we already know what W2 is. We've put it down at 72 degrees. We know what W1 is. It's 54 degrees. So now we know what this angle is. We can use opposite angles of a cyclic quadrilateral. Yes? So then we can simply say, I'm going to do number 4 right here. We can simply say that angle R is equal to 180 minus angle W1 plus W2, because angles in the cyclic quad. Okay, then we can simply just work it out. So then we know that that's going to be 180 minus W1, we said was 54. W2 we said was 72. Someone give me an answer for this quickly. Minus
54?
54.
54. Okay. 54 degrees. You guys with me? Yes?
Yeah.
Okay, fantastic. So that's basically how you go about solving the problem. So the whole thing again, remember, take the information I've given you, plot the diagram. Look at all the theorems you know, try and find the values of other angles before reading the question. Once you've done everything you can, read the question. And chances are, more than half the questions that they're going to ask you, you've already solved in the beginning. That makes sense? And then it makes everything tons easier. And circle geometry doesn't become that monster anymore, it just becomes that nice section that you sort of get tons and tons of marks on. In a past paper you'll find, at the end of this year, or even in June, you'll find they'll put 3 or 4 of these questions in, worth about 30 marks each. So there's tons and tons and tons of marks in for this section. Okay. You guys ready to do the next question? Hello? Yep. Okay, fantastic. So on the next page, there's one for you guys to try, question 9. Give that a bash. If you have any questions, give me a shout and then I'll get up and help you. Any questions now?
Yeah, but I
Okay.
just, yeah.
Okay, fantastic. Cool. Thanks, guys. Page 15, question 9.